Hi everyone, sorry about yesterday. I was a bit sick. So my goal is to talk about combinatorial commutative algebra, but it's a very broad subject and it has taken two different paths. And in my view, one path is characteristic free, is discrete, and the other path very much depends on the field. So I was hoping to just kind of talk about both. And to show a diagram I always think about, I always show it to everyone, but I find it's not very well known. It's also in one of my papers, but it's the only way I can always think about combinatorial commutative algebra. So first of all, the main object we have are monomial ideals. So that means the generators are products of variables. For example, x squared y, y, z doubled. Okay? And for a lot of, not for all practical purposes, but definitely for my practical purposes in this class, we can reduce to square-free monomial ideals. So, and this reduction is called polarization. So the end result is going to be like this: x prime, y, y, z doubled. So every time you see a variable that is squared, cubed, and so on, you just systematically replace it with enough many copies so that it becomes square-free. Systematically means you do so consistently in every generator, okay? So I'm not going to linger here very much, so I'm hoping during the problem session, some people will be looking at properties of polarization. So here, the end result is a square-free monomial ideal. And this has been of great value in combinatorics since the 60s and 70s. Some of the best results in combinatorics come from the algebra of square-free monomial ideals. And basically, the idea is that you're looking at a topological object, so a discrete topological object. You triangulate it, you get a simplicial complex, you associate it to it a square-free monomial ideal, and to prove topological or combinatorial properties of that object, you use the algebra of this simplicial complex. Okay, so this is in 60s, 70s, and to today, very popular topic in what is called now Stanley-Reisner theory. And the name you do not see here is Hochster, who's basically behind all of this. I'm going to mention Hochster. Hochster's formula, Hochster's ideas are what basically developed this. And then more recently, edge ideals, facet ideals, clutters, things like integer programming problems. Maybe I shouldn't write that here, but because that's not a topological thing. But so here, very much, the field characteristic plays a role. And in this area, it's pretty discrete. So it's all about counting. And this is kind of important because what you do usually, you look for classification theorems. You look for theorems that tell you what do all Cohen-Macaulay objects look like? What do all objects with such and such resolution look like, and so on? But in a sense, you have to be aware that you cannot do it in terms of edge ideals and facet ideals. Yes.
Someone near the door, turn on the lights above.
Oh. Okay.
That better? Okay.
Yeah, so a lot of things that people are looking for classification theorems might exist in here. Reisner's criterion for Cohen-Macaulay is an amazing one, which exists here. You cannot do it here. I've been working on this for years to just even translate it in this language. It's really hard, even though the objects are closely connected, but they're not connected via homology. Okay, so my goal is to basically tell you some of these definitions, show you how they're connected via a diagram I always think about, and show you some of the main theorems or classification theorems we have around Cohen-Macaulay, the Cohen-Macaulay property. So more specifically, I'm going to talk about Reisner's criterion for Stanley-Reisner complexes. I'm going to talk about things like whiskering and grafting, which gives you Cohen-Macaulay ideals, but does not classify them. I'm going to also talk about ideals with linear resolution and objects that show you linear resolution combinatorially, but again, can't characterize them. Some things you can characterize, for example, for very special cases of graphs or very special classes of monomial ideals. Some monomial ideals exhibit good homological properties independent of the characteristic of the base field, but this does not happen all the time, sadly. Okay, so let's start with so first of all, what is the Stanley-Reisner ideal and the facet ideal? So I am going to I'm going to try to be tidy with the boards, but I don't know if I can. So if I is a monomial ideal, actually, how many people here have never seen a simplicial complex? And Adam has never seen a simplicial complex. Okay. All right, so what is a simplicial complex? A simplicial complex that we look at is actually a geometric object, but I'm not going to give you a geometric definition. I'm going to give you an abstract definition, and that is take a set V is just a set. We want it to be the set of vertices of our simplicial complex. So let's call this simplicial complex, is set delta of subsets of V such that it's closed undertaking subsets. That means if F is delta in delta and G is a subset of F, then G is in delta. Okay. Can everyone still see here? Or should I switch boards? One more line. Okay. So for my one more line, I am going to give you a geometric realization of, as an example of what I just wrote. So here is an example of a simplicial complex. I use it, convex halls of points to draw it. So my vertex set is A, B, C, D. So that's my V. And my delta itself is the sets A, B, C. Actually, I'm going to write it like this. Actually, no, I'll write it properly. Sorry, I should make up my mind ahead of time. A, B, C, and all of its subsets. So A, B, A, C, B, C, more subsets, A, B, C, empty set, those are all subsets. All right, on to the next one, CD. And its subsets are C, I have it, D, don't have it, and empty set, which I have. So this is my simplicial complex. Okay, and usually I use, I think these are Claudia's chalks. I use this notation because all that matters is the maximal faces, the facets. So I usually denote this by A, B, C, which is the maximal face here, and the other maximal face is C, D. Once I know those two are there, I know all other faces. And all the elements of this set, as I was just saying, are called faces. And the maximal faces are called facets. So this complex has facets A, B, C, and C, D. Okay. And the dimension of a face is the size of the face, the number of vertices minus 1. And the dimension of the simplicial complex is largest dimension of its faces. Okay, so in this case, the simplicial complex that I had here, it has one two-dimensional face. This is a one-dimensional face. And these three edges are also one-dimensional faces, and the vertices are zero-dimensional faces. And the empty set has dimension -1, which is useful when you do homology. Okay, any questions here? Yeah. Yeah, let's think of finite simplicial complexes because we're always over polynomial rings. Yeah. Actually, I don't know if I've ever thought about infinite simplicial complexes. So, yeah. Any other questions? Yeah. Yeah, yeah. No, I don't. I don't. And I think it makes a difference in the Stanley-Reisner theory. If you don't require that, you get cones because you get these extra vertices give you cones. For facet ideals, you just, they just don't appear. So even though I usually do not, so this is usually causes a bit of a headache, the extra vertex. If some people assume all vertices are in the simplicial complex, some people don't. If you don't assume that, you get a bit of a problem with your topology and with your pictures, and you have to distinguish between, you have to distinguish between your pictures. So you make that decision when the time comes, basically. Any other questions? Yeah. Sorry? No, I want to. That's my dream. I can't. That's really hard. Yeah, but it's the same. So I'll tell you what I mean. Yeah, I tell you. Yes, you can. But the point is not the simplicial complex. The point is the ideal. Yeah. Okay, so that's a simplicial complex. You can think of a graph. A lot of you have worked a lot with graphs. You can think of a graph as a one-dimensional simplicial complex. Okay, so if I have a square-free monomial ideal, which is most of the ideals, when I do the LCM lattice and things like that, I will do non-square free. But again, polarization gives you square free. So square free is really enough for whatever we're talking about. But so if you have a square free monomial ideal, you can assign to it two different simplicial complexes. So one of them is the Stanley-Reisner complex. So the Stanley-Reisner complex basically is let's call this gamma. So sigma is in gamma if and only if sigma is not in the ideal I. Okay, so what do I mean? Let's try an ideal. Let's try the ideal I equal to let's do something simple. X, Y, Y, Z. Okay, so I have three vertices. Actually, this is one of those situations that, yeah, I have three vertices. So X, let me take a step back. Every variable, so first of all, when I say sigma not in delta, here sigma being in gamma means a set. And here sigma not in I mean the product of elements in the set. Okay. And this vertex set matters. The vertex set is the variables in your polynomial ring. Okay. So your monomial ideal lives in some polynomial ring, and the variables in that polynomial ring are going to be the vertex set. Okay, so here I'm taking I, which is x, y, y, z, inside the polynomial ring K, which K is a field, x, y, z. And here's where that issue that someone was asking about, I think Karen was asking about that, comes, that if you basically, do you just consider the variables that appear in your ideal, or do you consider all the variables in the polynomial ring? And for Stanley-Reisner theory, it matters to consider all the variables in the polynomial ring. Okay, so my vertices are x, y, and z, unless x and y and z appear as a generator of the ideal, but they don't in this case. And then the faces are going to be like x times y is in the ideal, so x and y are not connected. X times z is not in the ideal, so x and z are connected. And z and x, basically this is the picture. Z is not connected to x, and it's connected to y. So that's going to be your gamma. Okay, and the facet ideal or facet complex is sigma is in delta, so it's a facet complex delta. Sigma is in delta if and only if sigma is a generator of I. So in this case, we're going to get a graph. So again, we have xy and yz. So this is my delta. Okay. Sorry? It's on the same vertex. The vertex set is always the vertices. Yeah. Yes.
What about the non-maximum?
For this one, for the facet complex, well, they're in there.
But it's not that.
Pardon me?
Not that.
No, it's not a generator. You only take the generators, and you make your complex has facets that are equal to the generators. Oh, sigma is a facet of delta. Thank you. Yeah, sorry. Sigma is a facet of delta. It is, after all, called the facet complex. Thank you. And in this case, sorry, this is a graph. This is actually known. This ideal is known as the edge ideal of this graph. Facet complexes are just a more general version. Yes.
If I just I could just throw X, Y, Z into the ideal and just say that that's also another generator.
Right. So we're going to work based on the knowledge. That's an excellent question. One I should have, it's one of the questions, I guess, for the problem session. Here is a problem. All right, it's a fact. Every monomial ideal has a unique monomial generating set. Okay, which means that these complexes are uniquely defined. And same idea, this is a one-to-one correspondence. This is maybe I'm going to start my diagram here. If you have your ideal I, you have this gamma, which is the Stanley-Reisner complex of I. So I put an N usually. N means non-phase. Stanley-Reisner. And here I put an F, and I call this delta. This stands for facet. So this delta, this gamma is actually N of I. And this is N of gamma. And this is F of I. And this is also F of delta. You use the same operator because it's a one-to-one correspondence. Okay. Okay, so my goal is to complete this diagram hopefully today. So when I complete this diagram, I want to end up with the Alexander dual of I. Okay. So are there any questions so far? Sure, I said everything I wanted to say here. Okay, so if you start with a simplicial complex, from it you can make something called its cover complex. And the cover complex is basically has facets that are minimal vertex covers of your simplicial complex. So if delta is a simplicial complex, the cover complex, okay, I call this delta M, but I have no idea why I call it delta M. Adam, what do you call the cover complex? You don't have a name for it? Okay, delta M. I expected someone to complain. If anyone has a better name for the cover complex, please let me know. I called it delta M many, many years ago, and I think I did at least. So we'll say delta M. Delta M is a simplicial complex whose facets are minimal vertex covers of delta. Okay, so what does that mean? A minimal vertex cover is the smallest possible subset of vertices so that every one of your facets is incident with it. So a minimal subset A such that every facet of delta is covered or incident to A. Okay, so for example, if I look at this picture here, I look at my minimal vertex covers. Okay, and my minimal vertex covers here are Y, because every facet has Y in it, and X comma Z. If I pick X, I can't pick Y anymore because that would make X redundant, so I pick Z. So it will be XZ. Okay. So the cover complex, delta M, is going to be Y xz. Okay. I was going to show you something very cool, but the example I picked is hiding what is very cool. I'll show you anyway. Every facet here is a complement of a facet here. I will write that in the diagram. In this case, they look the same because there are only 3 vertices. Okay, so I'm gonna put delta M here. And this is what I call the cover. And this is a duality. So fact problem. Okay, so that's the duality over there. And another thing I was just telling you about was, I'll do this one is orange. So another fact problem. Is that delta M complement is gamma. So what does delta M complement mean? Maybe I'll write gamma complement as delta M because this, by definition, is set complement of the facets of gamma. F complement. This is set complement. Where F is a facet. Okay. Yes, yeah. Okay. So here's another fact problem, and we can do an example of that here. The minimal vertex covers are actually coming from the primary decomposition of your ideal I. Okay. Minimal vertex covers of delta are generators of minimal primes of F delta. So if you don't know the primary decomposition, don't worry about it. But I assume at least half people here do know the primary decomposition. In that case, please do check that. The point really here is the real thing to check is that if you have a square-free monomial ideal, the primary decomposition you will have no embedded primes. You only have minimal primes. And the minimal primes by definition are going to be just the way you pick exactly the smallest number of vertices that covers every facet, which is, yeah. But, you know, basically, if I want to ask Macaulay to, I know Macaulay to has scripts for doing stuff, but when I want to ask Macaulay to do a Stanley-Reisner complex for me, I just do a minimal, because I don't remember all the commands. I just do primary decomposition, and that's what I use basically. And I take the complements. Any questions? Okay, so here we are this far. Yeah, so another duality that exists on the Stanley-Reisner side is Alexander duality. which is, I'm going to call it gamma dual. This is a topological duality. It turns homology into cohomology. So it's far from discrete. The primary decomposition is very discrete. It's always the same. Alexander dual of gamma is sigma or sigma bar, where sigma naught is not in gamma. It has a funny, too many knots in it. It's the complement of all the non-faces of gamma. Let me double check. I hope I wrote this down somewhere. Someone who does Alexander duality, did I get all my knots correct over there? That's it, right? Yeah. Okay, that's also a duality, gamma dual dual. Gamma is gamma dual, and gamma dual dual. This is another fact problem. Gamma dual dual, I'm going to write it also in green. Gamma dual dual is gamma. That's the complement. Didn't I define it? I thought I did, but thank you if I didn't. Set complement. Set complement. I'll write it again. Set complement. Okay, and so happens that these two are also complements of one another. So what I'm saying is that if gamma dual has facets, G1 to GT, then this one has facets G1 bar to GT bar. And if this one has facets F1 to FQ, this one will have facets F1 bar to FQ bar. This is a really useful correspondence, okay? All right, and at the bottom of my diagram is the fact that if you take the Stanley-Reisner ideal of gamma dual, or you take the facet ideal of delta M, you get what is known as the Alexander dual of I. Same ideal. Okay? Yeah. I probably defined it wrong, so let's.
So I know how to take, so if I take the complement of a facet, then I'm taking the minimal prime, I take the product of those generators. So that sounds like I want sigma in delta, and I take it set complement.
No, I think you wanted not in delta. I remember it has two knots.
Okay.
Yeah.
Thanks.
This is the challenge of the problem session. Prove me wrong, which is easy, but yeah. Someone can look it up, please. I wrote it down because I usually get this wrong, but what I remember always, there are two knots, and there are not too many possibilities of knots, right? So there are only two. Yeah. Any other questions? How am I doing in terms of time? I don't know when I started. Okay. All right. Well, we're not doing too badly. Okay, so Okay, so this is basically the correspondence between this side is Stanley-Reisner theory. This side is facet ideal theory. And edge ideal theory and clutter theory. This side has homology. Has homology, whatever that means. This side, as far as I know, has no homology. I don't know if that's really true, but it's, yeah.
Wow.
Yeah.
Just the complement of the second sigma. That, assuming their definitions of the so sigma such a complement.
Isn't that equivalent? I'm happy to change it. Doesn't it mean the same? Sigma such that sigma bar is not in that. That's the same, no?
It's sigma bar, not a gamma. Sigma bar is sigma.
I had it right? This is right too, right? Yeah. Sorry, Trisha.
I had an extra not going to the ideal. Sorry.
That's okay. You're thinking at a much deeper level. See, I was just thinking 2 knots. Yeah. All right. So I'm going to start talking about this. So like I said, a lot of what I will tell you about is criteria on this side. And they translate only to conditions on this side because this side doesn't have a homology theory built into it, okay? So the first thing I want to talk about is Reisner's criterion of Cohen-Macaulayness. So maybe I will also write some of these here. There exists criterion for Cohen-Macaulayness. There exists formula for Betti numbers. And resolutions. Among many other things. Here, really, this whole area was developed because of, in the area of Riesz algebras and integral closures and finding normally torsion-free ideals and things like that. So it wasn't even made for the homology theory to begin with, and people started later studying that. So anyone who can bring any homology from that side to this side, that's going to be a really nice contribution. Okay, so let's start talking about Reisner's criterion. And for that, okay, maybe I should write this properly. Cohen-Macaulayness. So an ideal is called Cohen-Macaulay if the depth of the ideal is equal to the dimension of the ideal. Okay, so let's take I, let's let it basically any ideal I, but we're gonna stick to our square-free monomial ideals. Is Cohen-Macaulay if depth of R mod I is equal to the dimension of R mod I. So the depth is, I'm not going to linger too much. I'm going to just say what it means. It's the depth is length of a maximal length of a regular sequence that you can find in this ring. Okay, so this is a maximal length of a regular sequence, which means a sequence of non-zero divisors. So it's going to be, let's call them theta 1 to theta t. And it means that theta 1 is a non-zero divisor on R mod I. Theta 2 is a non-zero divisor of R mod I plus theta 1. All the way, every theta I is a non-zero divisor on R mod I plus theta 1 to theta I minus 1. That's what it means. And this one, the dimension is the maximal maximal height of maximal length of a chain of primes. Okay, and just so that you know, this is pretty cool. This is a discrete. I always like to look at things whether they're discrete or non-discrete. Discrete meaning that this is going to be always the same no matter what your field is. But this one depends on K. I guess hidden here is that my polynomial ring is always a ring of polynomials with coefficients in some field. And what is happening depends on what field you're taking. Is there a question there? Yeah.
So the usual definition of Cohen-Macaulay that I know is that like all the localizations are CF like, and I always forget how depth and stuff works over polynomials. So is that definition the same?
There are many definitions of Cohen. This is the standard definition of Cohen-Macaulay. I don't want to actually, I want to give Reisner's criterion. For us, it's going to be Reisner's definition. Yeah. Yeah, but the thing about Cohen-Macaulayness is that it's a really beautiful property. It's hard to detect, but in every setting, it gives to a very nice definition in your setting. So, yeah. I'll be looking at Cohen-Macaulay simplicial complexes. So for that, now I have to figure out how to do these. Maybe I will use this. Oh, I have another one here, and then I'll go to this one. So Reisner's criterion for Cohen-Macaulayness. I'm going to first write it, and then I will try to tell you what each component means. So I square free monomial ideal in R, which is K of x1 to xn. And gamma is n of I, which is the Stanley-Reisner complex of I. Then gamma is Cohen-Macaulay. Actually, I is Cohen-Macaulay. Combinatorials say gamma is Cohen-Macaulay, but I is Cohen-Macaulay for us in algebra, if and only if the K dimension of the hi of link gamma sigma is 0 for all I less than the dimension of the link and for all sigma in gamma. Okay, so I will translate all of this for you, hopefully. But the beauty of this is that it's a criterion. And when I say there exists a homology theory for Stanley-Reisner theory, I mean simplicial homology theory, which is a translation of our regular algebra homology theory, which was done really by Hochster. So Reisner was Hochster's student, and this was his thesis, the criterion. And the criterion for Cohen-Macaulayness that he gave for his thesis basically enabled huge advancements in combinatorics. And the advancements had something to do with counting numbers of faces of this and that combinatorial objects. So you would never think that homology theory and Cohen-Macaulayness would come handy, but it did. Okay, so let me describe to you what a link is and what simplicial homology is. So this is reduced simplicial homology. And this is link. Okay, and it is 1023. So I'm not going to be that ambitious. Let me first tell you what link is. So if gamma is a simplicial complex, and sigma is a face of gamma, the link of sigma is in gamma is going to be all other faces that whose intersection with sigma is empty and whose union with sigma is in gamma. That's all it is. Okay, so if I have x, z, u, the link, this is my gamma, the link in gamma of y is going to be x, z, and u. Okay? Because y union u is a face, y union xz is a face, and none of them intersect. Okay? And simplicial homology. Simplicial homology is a bit more complicated. But Claudia talked about cycles and boundaries. So cycles and boundaries are exactly what are used here. Our cycles are going to be cycles of faces coming from faces of a special dimension of a simplicial complex, and the boundaries are going to be boundaries of those faces. So if delta is a simplicial complex, Ci of delta is going to be, I'm going to do a vector space version because we're doing vector spaces here, is a K vector space. So let's make K be a field. So it's a K vector space spanned by I-dimensional faces of delta. Okay? And so you can always find there are boundary maps sigma I going from, so sigma I plus 1 from Ci, so this is really Cik, Ci plus 1 delta over K to Ci delta K, which takes really every face, because the basis for every one of these CIs is going to be your faces. So what matters is what happens to every face, and every element is just a sum of faces. Okay, so takes every face to its boundary. So what is a boundary? I'm going to do an example here. Like, for example, an edge goes to these two, A, B, goes to A minus B. Okay? And a triangle this is, an edge is the smallest simplicial complex of dimension 1. It's a 1 simplex. Smallest means smallest in terms of number of vertices. A triangle is the smallish simplicial complex of dimension 2. So A, B, C. What I'm going to do, so there is a proper algebraic definition where you orient everything, but we don't have time for that. So I'm going to just give you a gist of it. E1, E2, E3. The map is going to take the triangle to the sum of its boundary edges. So alternating sum. So E1 minus E2 plus E3. The plus or minus are a little bit arbitrary, meaning they come from picking an order on your vertices of the simplicial complex and then sticking with that order. That's the most important thing. You pick any order you like and you just stick with that order. That means if A is before B, then you do B minus A. Okay, so you just stick with that order. Okay, so these chain maps, this is actually going to give me some long sequence, and its homology of these, it's going to give me a simplicial chain complex. So if delta is a d-dimensional complex, I get a simplicial chain complex which is basically has to go from CD, what did I call this, D, all the way down to C1, C0, and even C-1 for the empty set, because we do the, let me not put a 0 there, because we're doing reduced homology. And the homology of this is going to be the kernel of each boundary map mod the image of the previous boundary map. Of course, this is a chain complex, so maybe problem / fact for everyone to check who hasn't seen this is that, I hope I write this in the correct old order, that this is in fact a chain complex, meaning that if you compose two of those maps sequentially, you're going to get 0. So that's your homology, and it basically keeps track of holes. So it tells you when you have a triangle that is not filled, or a tetrahedron that is not filled. So we'll talk about that more. Yeah.
Sorry, for reduced, don't we omit C minus 1? Got that backwards.
No, we don't, right? For reduced, we don't, and for non-reduced, we do. Can I put a question mark because I'm out of time?